Okay, thank you very much. Thank you for the introduction. So, yes, my talk will be devoted to colorings of random hypergraphs. And this is joint work with two of my students, Dmitry Kravtsov and Nikolai Krochmal. So let me start with some definitions. Maybe all of you know them, but let us recall some of them. So what is a hypergraph? Hypergraph is just a pair of two sets, V and E, hypergraph H, where V is a finite set called the vertex set of a hypergraph, and E is some collection of subsets of, not E of course, but V, which are called edges of the hypergraph. So we have vertices and some collection of subsets, edges. Hypergraph is said to be K-uniform if every edge is a K subset, so every edge consists of K distinct vertices, so if K is equal to 2, then we have a just graph. And we will consider vertex colorings. So a vertex coloring is just a mapping from the vertex set to set of colors. If the number of colors is equal to R, then F is called NR coloring. So these are basic definitions. So we will consider random hypergraphs. Let me recall the binomial model of a random K-uniform hypergraph H of NKP. So we have n vertices, and we consider n vertex K-uniform, complete n vertex K-uniform hypergraph, and every edge of it is included independently with probability P into our random hypergraph H of NKP. So roughly speaking, we have a Bernoulli scheme on the edges of n vertex K-uniform, complete n vertex K-uniform hypergraph. And we will consider panchromatic colorings. So a vertex coloring with R colors, and R coloring is said to be panchromatic for a hypergraph if every edge meets every of our colors under this coloring. So in every edge, we should have a vertex of every color. So if we have, say, 3 colors, then we should have a vertex colored with 1, another vertex colored with 2, and then one more vertex colored with 3, and all the others can be colored arbitrarily. So, and here is the question, the main question. So we want to find for given fixed numbers R and K, R should be less than K, otherwise it's not. Maybe it can be equal to K, but we will consider less than K. Find such functions, probability functions P, for which our random hypergraph admits a panchromatic R coloring with probability, with high probability, with probability tending to 1, as n tends to infinity. So we have number of colors, K is they are fixed, and P is a function of n. Okay. So what can we say about this? It is easy to see that this property, admitting panchromatic coloring, it is monotone. So if we have a coloring for a hypergraph and we remove some edges from it, then the property will be still satisfied. So it has a threshold probability. This is a general result from the theory of random subsets. Moreover, in our case, we have a very nice result by Khatami and Molloy, which says that this property, admitting a panchromatic coloring, has a sharp threshold. What does it mean? It means that there exists some function p hat such that for every positive fixed epsilon, the limit probability for the event that our hypergraph admits a panchromatic R coloring, the limit probability is equal to 1 if p is less than 1 minus epsilon p hat. And otherwise, the limit probability is 0 if p is greater than 1 plus epsilon p hat. So if our probability is a constant time less than the threshold, then we have a limit 1. Otherwise, if we up, our probability is greater by some constant, by a constant greater than p hat, then we have 0. And so we can ask more natural question: how can we find or estimate this probability threshold function p hat for the property of panchromatic arc colorability? So this is the main question, and we will try to answer it. So, okay, let us start with two colors. Okay, the least possible number of colors is 2. So what is panchromatic two colorings? Panchromatic two colorings are just usual proper colorings. So if you have just two colors and you consider that every edge should meet every color, then all the edges are not monochromatic, right? Because you have both colors in every edge and nothing else can be said. So this is just the same. And the question of estimating two probability threshold for random hypergraphs was initiated by Allen and Spencer. And they showed that this probability corresponds to the sparse case. What does it mean, sparse case? So in this case, we have a linear number of edges. So our probability P is equal to constant times n divided by n choose k. So if you can calculate the expected number of edges in our hypergraph, it will be equal to Cn. And C here is a positive constant. And in this case, we can reformulate the problem. So in fact, we are interested in estimating P, but for such sparse case, we can just estimate this constant C. So we have just one parameter. So another parameter, which is easier. So in this, so for given fixed R and K, we would like to estimate or even find, if we were lucky, the threshold function C hat now. So P hat will be equal to C hat times n over n choose k for the property of panchromatic arc colorability. And what is known? So Allen and Spencer proved that it is, so in the sparse case, we have a threshold. So they showed that if k is large, maybe, or even fixed, and p is equal to Cn over n choose k for given positive constant c, then we have two cases. So our random hypergraph is not too colorable with probability tending to 1 if our constant is greater than this expression. So 2 to the power k minus 1 log 2 minus log 2 over 2 plus something tending to 0 with growth of k. And on the other hand, it is too colorable with high probability if c is less than 2 to the power k divided by k squared. So we have a little bit, some gap between upper and lower bounds. So this is upper bound for our C hat from the previous slide. So C hat should be, C hat lies between these two bounds. Yes, right. So, and so we have some gap. Few works was devoted to removing this gap. First of all, the first result was obtained by Akhleptos, Kim, Kavrelevich, and Titali in 2002. So they proved that this lower bound can be improved to 2 to the power k over k. And finally, Akhleptos and Moore in 2005 obtained by using the second moment method. We will discuss this method a little bit later. If they improved the lower bound up to the following expression. So we have almost the same. So 2 to the power k log k minus log 2 minus 1 over 2 plus something tending to 0. So the gap is very small. So we have just a constant gap between the upper and the lower bounds. So 1 over 2 plus something small. Okay, this is good, but we can go further. Kojoglan and Zdeborova in 2009 improved 1 over 2 by log 2 over 2. So here I just write minus log 2 over 2 twice, but just to show that there is an improvement here. So log 2 is smaller than 1. And they conjectured that the threshold value has the following order. So we should have not log 2 over 2, not 1 over 2, of course, but 1 over 4. So our C hat should be of the form of this form. And there is a nice correlation between two problems. One of them we discussed before, so it's just two correlability over random hypergraph. And one more problem comes from theoretical computer science. So it's just random, not all equal k-sub problem. I will briefly recall this problem. So we have two integers, k and n, and we consider a random Boolean function of n Boolean variables, f of x1, xn. So this function has a very special form. So it is equal to the conjunction of m disjunctions. So C1, Cm are disjunctions. They are independent and random disjunctions of k randomly chosen variables or their negations. So every disjunction consists of k elements, and every element is chosen independently and randomly. It is either a variable, x1 from the set x1, xn, or maybe it's negation of these variables. So the function is satisfiable if there is a vector epsilon n from 0, 1 to the n, such that f of this vector is equal to 1. So we have some values of our random of our variables such that the function is equal to 1. So for our special case, it means that there is no disjunction. There is no disjunction with all zeros. So if every element is equal to 0, then okay, everything is 0. And in not all equal case, we should have almost the same, but we forbid also disjunctions with all ones. So our function is not all equal satisfiable if there is a set of values such that our function is equal to 1, but so there is no disjunction with all zeros. But moreover, there is no disjunction with all ones. And we are interested in estimating the threshold function, for which we have the following. So recall that m is number of clauses here. So if m is greater than 1 plus epsilon times this threshold times n, then the limit probability, and so the function is almost surely not all equal k satisfiable. And the limit probability is equal to 1 if m is less than 1 minus epsilon times this r hat times n. So we want to estimate this threshold function, and Kojoglan and Panagiotou in 2011 proved that the conjecture for random hypergraphs is true for random not all equal k-sub problem. So we have this estimate for our threshold function r hat. So it has this form plus something tending to 0 exponentially with growth of k. So the problems are almost, they looks very very similar, and I think that one can just using this result prove that for two probability we have almost the same threshold. So we can consider that the problem is solved for two colors, I think. And in our work, we were interested in the case of a larger number of colors. So, and we just for simplicity consider the case of 3 colors. And here is our main theorem. It says that we have the following lower and upper bounds for the threshold for the property of panchromatic 3-colorability. So this is the upper bound. So we have log 3 over 3 times exponent 3 over 2 times k to the power k minus log 3 over 2 plus something tending to 0 exponentially with growth of k. If c is greater than this, then we do not have panchromatic 3-colorability with probability tending to 1. And if c is less than almost the same, minus another error term, then we have panchromatic three-colorability with probability tending to 1. So the bounds are very tight. So we have an exponentially small gap between them. Now some ideas of the proof. Maybe it is the most interesting case because it's very natural to expect that the results will be the same. So for the case of two colors, I have already said, so by using the second moment method, Chloptes and Moore do not get very tight bounds. So they had a constant gap. So this upper bound can be proved straightforward by using the first moment method. So it's very easy, and I will skip any details about it. So let us talk about the lower bound and the proof by using the second moment method. So recall that we have a sharp threshold for our property, panchromatic three-colorability. So we have this very special function p hat. And but okay, we don't know what is it, so we want to estimate it. But in fact, since if we want to prove the lower bound, so it is sufficient to show that under the condition of the theorem, we have the following. So our probability is not equal to 1 in the limit, but it is bounded from 0. Why it is sufficient? Because if we have this, so the limit probability is bounded from 0, then for every smaller constant c, so this c, for every smaller constant c, the limit probability will be equal to 1, because we know that we have already passed the threshold. This function, so this cannot be lower than the function p hat, because we know that the constant time smaller, because we know constant time greater, because we know that we are bounded from 0. Okay, so it is easier, of course, just to show that it is bounded from 0. For proving this, we will consider another model, which is uniform, in fact, uniform model over a random hypergraph instead of binomial model. So we consider a random hypergraph H of nkm, where in which we choose m random independent edges. M is equal to Cn, of course. The number of edges will be the same. And in every edge, we choose k vertices also randomly and independently. Why? It is much easier to calculate something when you have independence. So we will choose vertices also randomly independently. Maybe it can be bad because, okay, our hypergraph can contain duplicate edges, so the number of edges, distinct edges, is not always equal to m, of course. And it can even consider non-proper edges with coinciding vertices. Some vertices can coincide, so in fact, the length of our edge is not k, it can be less. So maybe it is even every vertex of an edge can be the same. So we cannot, such an edge we cannot color panchromatically, but it will happen with probability, with tiny probability tending to 0. And it is easy to show that if we can color this random uniform model, so if this hypergraph admits a panchromatic three coloring with high probability, then for, say, for constant c, then for every smaller constant in the binomial model, we will have the same. So it will be panchromatic three colorable with probability tending to 1. Okay, now we deal with uniform model. So we want to show that there is panchromatic three coloring, and we will try to find it by using just balanced colorings. So a three coloring is called balanced for n vertex hypergraph if the cardinality of every color class is equal to n over 3, just maybe upper whole part or maybe a lower whole part, but just n over 3. So the number of vertices colored with 1, with 2, and 3 are the same. And it can be shown that it is sufficient to prove theorem only when n is divisible by 3. So we just have n over 3. The coordinate of every color class is equal to n over 3 without any whole parts. So, okay, and let us consider random variable xn, the number of panchromatic balanced 3 colorings of our random hypergraph in uniform model. Then, of course, the probability that our hypergraph admits a panchromatic 3 coloring is at least the probability that this random variable is positive. Okay, how can we estimate this from below? This can be estimated from below by using the Paley-Zygmunt inequality, which says that this probability is at least the ratio between the first moment squared and the second moment. So all we have to do is to show that the second moment doesn't exceed the first moment squared times some function depending only on k. So if we prove that, then this ratio will be at least some function depending only on k, and the limit probability will be bounded from 0. So looks very easy, so we have to calculate the first moment, the second moment, and compare them. Okay, nothing else. But probably it is not very easy. So the first moment can be easily calculated. So just by using simple observation, so our edges are independent, and with this probability, every edge is colored panchromatically under every balanced coloring. So we have this number of balanced colorings. So this is probability. So probability should be in the power of the number of edges. And applying Stirling formula, we obtain this expression for the first moment of the random variable xn. So here we have some exponent, n times some constant, and 1 over n in front of the exponent, a polynomial factor. Okay, now we have to calculate the second moment. So suppose we have 2 balanced colorings of our hypergraph. Here we have to consider the values of aij. Aij denotes the number of vertices colored with color I in the first coloring tau, say, and with color j in another coloring tau prime. Okay, so we can consider a matrix A, 3 by 3 matrix with elements aij. And since our colorings are balanced, we have a very nice property for our matrix. So the sum over every row and every column is equal to n over 3. So after some normalization, we will get a double stochastic matrix. So it's very nice. So let us consider the set of all such matrices. So recall that aij is not it cannot be negative, so it is non-negative. So we will have a double stochastic after dividing by n over 3. Okay. Now we can calculate the second moment. So the second moment is equal to the following expression. We have the sum over the matrices. So this comes from, so we have to choose the vertices colored with every color in both colorings. So, and this is probability that our random edge, any random edge, is colored panchromatically in both colorings. So we have 2 colorings, so there should be panchromatic in both colorings. So, and again, power of the number of edges. In the power, we have a number of edges. After a few transformations, we obtain this expression. So we will have the first moment squared times some polynomial factor, n to the power 5 over 2. And again, the sum over matrices. So here, this remains after application of the Stirling's formula, and we have some exponent. In the exponent, we have the difference between the functions f and g. So f is this. This comes from again. This function comes from the Stirling's formula. So we have some entropy-like function, and g of a is this. So where h is a very long expression here. Okay, so looks not very simple, yes, just to calculate what is it. But in fact, all we have to do is to prove this crucial lemma. So we want to show that for every matrix A, from our special set of matrices. So we have the following inequality between the difference for the difference between F and G. So it should be at least this sum of squares, aij divided by n minus 1 over 9 squared, sum over all ij, times some function depending only on k. So, okay, this is just technical, so you have to prove by using simple calculus. If you succeed, then the proof can be finished very quickly. All we have to do is to show that the second moment, in this case, can be estimated from above by using by this expression. So we have again the first moment squared times this sum to the power 4. Why it is possible to do? Because after applying this lemma in our expression here, we will have a product of 9 factors. Every factor will depend on aij, so we have 9 factors. And since our set of matrices is very special, so in fact, in a matrix we have not 9 parameters, but just 4, because the sum over every row and every column is fixed. So you can consider just 2 by 2 matrix, say for I and j from 1 to 2. And so you can choose it arbitrarily, and then everything else can be is defined uniquely. Okay, but this expression, every factor can be estimated from above by 1 over root n. Then okay, we have 4 factors for 4 parameters and 5 free factors, and these free factors will destroy this n to the power 5 over 2 in front of the sum. Okay, after that we will have this. This sum can be easily estimated by an integral, and this integral, it can be easily checked again so that it converges, and it can be estimated from above just by some function depending only on k. In fact, it depends only on this b, but b depends on k. Okay, so this is the end of the proof, so all you have to show that this inequality holds for every matrix. Okay, so let me make some conclusions. So we obtained a very tight bounds for the panchromatic probability threshold of a random hypergraph by using second moment method. Quite surprising it works because in comparison with the case of 2 colors, in the case of 2 colors you cannot do this, so you will have a constant gap. And I think that our approach to the second moment method is rather simple and flexible, so it can be applied for another type of colorings, and it can also it's easy. So all we have to prove is just this inequality, and it requires only simple calculus. So yeah, I would like to stop here. Thank you for the attention.
Okay, formally, we probably don't have time for any questions, but I suppose let's do it anyway. So maybe some questions or comments for the talk?
Could you please talk into the microphone? Better in hours, because this one is not working properly usually.
just to understand, for two colors, if you do the same thing, you don't get this variational
Yeah.
problem which you can
Right.
solve, or I see. So it just doesn't work.
Yes, it will lead to the bound of Achloptis and Moore.
I
Just
see. And for more colors,
Uh,
it continues to work as nicely.
so if you consider proper colorings, you will have the same constant gap between the upper and lower bounds. For panchromatic colorings, surprisingly, we obtained a very small gap, exponentially small. So it was quite surprising for us. So I think that okay, for 4 colors, for panchromatic colorings, I think it should be the same. But when the number of colors will grow and more or less say root k, I don't know, maybe it will not be easy, because in this case you have to consider to find some maximal summand in the inclusion-exclusion formula. It cannot be easy, I think, for large number of colors.
Now I have 2 microphones. No, only one. Okay, let us thank the speaker once again.